that in, and I know it's a constant. So that's what this C is that I put in. And so that's, you can see it as the floor of whatever. So as long as I remember that. And if we approximate, so if we integrate from A to B x, and we look, okay, what does this do as a series? Well, see, here's the normal integral. So that's made for to display that, just so that we can see. Well, here it is. And this is the error that we make by looking at scale delta. So this h delta, in this case, is very, very, very explicit. And this c here is kind of the ringing you get by approximating with different deltas. The different delta will work differently depending on how close it is to a multiple of b minus a. And that's exactly what this says, is if you're an exact multiple, then c is 0. Otherwise, it gets closer and closer to 1, you're halfway, and then it jumps again. So this is kind of some ringing constant. And it says, well, the rectangle rule converges linearly in delta, in the scale, in exactly this way. Let's try other stuff. So for quadratic, so the first one is quadratic, so x squared between 0 and 1, just so we see less things. And it's, of course, 1/3 as we're expecting to, and because it's the rectangle rule, it's linear convergence again, plus other stuff behind. Right? You get great big messes if you throw in a whole lot of symbols, but you still get the answer that you're expecting is the leading coefficient, and the rest just tells you how well it approximates. For a constant, the only reason we don't get the exact answer is because we're going every delta, so we're forgetting some part. So if I use a different integration process, then that changes. And it works for exponential as well. There's no big surprise there. So we really haven't done very much. All we've done is logically shove things around. All we've done is peered into the process of integration and really asked it very closely, how do you converge? And it's telling us how it's converging. The interesting part is when you ask it, how do you converge, when it doesn't. Well, it tells us, parallel thinking, hey, it's singular. You added up when you started at the singularity. No good. Hey, dummy, don't do that. Because you're evaluating a singularity. So all I'm doing in this approx 2 is that there's a +1 over here. I'm not integrating at the singularity. Let's see what that does. Well, for x squared, basically it doesn't change anything. Right? No problem. So it's fun when you try it. Let's not show too much. Right. For 1 over x. 1 over x, where are we? We're at the bottom. Integration gives us infinity. Integral from 0 to 1 of 1 over x is infinity. We're happy. Here's where it's interesting. Gamma, the constant, hey, there's a log delta. It's diverging. That's, you kind of expect 1 over x when you're trying to sum things up, it's going to diverge like logarithm. Well, there it is. And after that, well, there's noise. Right? That's exactly what you expect. That's the interesting part here. It's telling us exactly how it's divergent. It's much more interesting. Right, I'll put the C back, just for fun. Right, there we go. So 1 over x squared, it's still diverging. The interesting thing is the constant is kind of fun. Pi squared over 6 out of, I'm actually doing a finite sum here from 1 to n, from 0 to n minus 1. And I got a pi squared over 6 out of that. It's kind of fun. But I did do an asymptotic approximation. There's no miracles. And then really, -1 is kind of an interesting constant to come out on top. But it's telling us very much that integrating this from 0 to delta diverges at that speed. So if we're going to get something, if we have something else that diverges at that speed, and we add them together, they're going to cancel. This is what we'd like, but we want this to make sense. For x cubed, we get zeta 3. Now, let's not get carried away. The zeta is not magic. So what I'm going to do is, in this slightly different one, this is the same thing as before, and I'm going to add one more term. I'm going to sample that delta over s, where s, I'm going to imagine, is going to be between 0 and 1. And so I'm going to weigh that properly, because it's going to be the part. So I had chopped things up like this at delta, and I added all over here. Well, I'm going to also look at this chunk over here and add that in. Try to sneak a little closer to my singularity. And look at 1 over x cubed. Oh, I get the s. S doesn't show up here at all. The only place it shows up is in the head term of the close to the singularity. And we still have our zeta 3, but we've modified it by an arbitrary s. Zeta 3 is not really all that. It's not magic that it came up, because I can make it whatever number I want by just picking s. It's pretty natural. Anyways, now, if you can see the answer. If I try to go from -1, 1, which is kind of what you really want to do, you want to integrate across that singularity. And you'd kind of like it to come out to be 0. And you just, please, give me the answer. It comes out with this thing here. It's 0 sometimes, but sometimes it's infinity. This is nat cos over delta. Ooh, 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 ooh. That is nasty. Nasty, nasty, nasty. But you look at it and you go, well, of course. When you're sampling like this, you're kind of getting a little too close to the singularity. And then as you increase delta some more, then you go further away. And you keep expanding like that. And yeah, the process diverges in a totally random way. This is bad. This is not a good process. So we have to fix it. Right? So that's what we get. So let's look a little, further down to see what's really going on. Right. So if I evaluate that sum and I actually look, I don't do the series. Let's give me the sum that I asked for. Maple is quite happy to give this psi 1. So the nice, beautiful function. But really, it's singular in a whole lot of places, because I've asked it to sum up things in a bad way. What I really want to do, I can't willy-nilly ignore singularities. What I really want to do, so if I'm integrating from A to B, and I know I have a singularity here. Let's color chalk and put it down. It's probably right over here. I kind of want a little exclusion zone around the singularity. And of course I'm going to make it with delta, or 2 delta, or whatever. Up at my scale, I'm going to say around the singularity, let's avoid that, and then make the scale smaller. Yes?
Should one ask, is it impolite to ask what you mean by singularity? To ask what you mean by singularity.
In this case, I pretty much mean anything that goes to infinity. Plus, minus.
Algebraically?
It can be much, much, much nastier. So really, the only thing at this point that we care about is this h delta, can we make an asymptotic expansion of it at 0?
And you don't want oscillations.
We don't want, yeah, oscillations, that's just, we're not getting a good control over anything if it's oscillating like that. So oscillations are what kill us, like kill this left, right, and center. Have to be really careful. Right, so we put a little exclusion zone around it, which is kind of what this code here does. And it's complicated, I don't want to get into it, but basically S is going to be my set of singularities, and I'm going to try to symmetrically go back and forth between the singularities. And so this should also remind you of Cauchy principal value. Cauchy principal value looks, so if I was going to do the integral from -1 to 1 of 1 over x dx, for example, or x some function, I would actually look at the limit as epsilon goes to 0, minus epsilon, epsilon. Okay, because this one goes to infinity, this one goes to infinity. What you really want to do is put them both together, and as a function of epsilon, take a look at how that goes. So this is the definition of Cauchy principal value. In this particular case, you get 0, which is kind of what we'd like to get, because contradicting Cauchy is a bad idea. So let's see if we can get that. So if I try, right, so just to not mess ourselves up, I did 1 over x minus a between 0 and 2a, because if I do it, if I do 1 over x at 0, strange things happen, and I just didn't want to get into that mess. And we get the size. Again, no problem. Asymptotically, this is 0 in delta. This is the answer we expect. We're kind of happy with that. And now it turns out that this is all okay, because pretty much all of this, like two of those terms are singular. And really what those psi's are a sum from here to infinity minus a sum from somewhere else to infinity. And these two infinities cancel. This is all very, very delicate. So the fact that the asymptotic series cancels out beautifully is symbolic magic. In general, it's very, very finicky. And so at this point, I'm going to stop with the examples, because if I try to show you different ones, I'm going to give you, it's going to, all sorts of messes will come out, which turn out to be okay, but we do computation after computation after computation to show that they're actually okay. However, I can surely see one of the ones that I will show you one of those. So 1. So 1 over x squared minus 1 to 1, scale delta, Winging constant c. We tell it the singularity at 0. And if we try to compute the series, we get this rather beautiful mess. If we actually, we can make it a little bit better. By simplifying every term. A little bit better. So the big O term is not much better, but the first term is a tiny bit better. It's got all sorts of ringings there, but at least it's telling us that it's diverging at the leading order, like 1 over delta, which is kind of what we expect. And this stuff, sometimes it's actually 1. Fairly frequently, this is actually simplifies to 1, but it's a lot of work to do so. And I'm still working on, when does it not? and I'm still refining the integration process to show that with proper integration processes, this is actually one, or a constant, so that it's not ringing. And what's really important is that it diverges like this. But because it's rigged up the way it is, you're kind of summing in here and summing here, and it's a finite sum of terms, and you're looking at the speed that this process is converging or diverging. Really, you know, I'm summing in a finite number of terms, I'm summing a finite number of terms, that's scale delta, and then I'm looking, okay, as I make the scale go down, asymptotically, what is going on with this process? I'm not integrating anything. I am taking one infinite process, but I'm looking very much at the speed of convergence. So, but because it's a finite linear process, we easily have that, like the integral over here is like our summation process over here is equal to the summation process here plus the summation process here, pretty much by definition. So of course we get extra linearity that we didn't have before, because if the whole thing converges but each piece diverges in a controlled way, we've won. We've now integrated something that before we couldn't, just because of a pesky singularity that we knew was not a big deal anyways. So as long as this at scale delta, things diverge in a controllable way so that we have an asymptotic expansion, then we're okay. Now, we can construct all sorts of functions where the scales at which this process diverges or even converges is very, very strange. And so effectively, you can't, you don't get any more with this, because this function is just too nasty. This isn't, I'm not trying to sell you a miracle here. This is just a very interesting observation that if you dig at the process of integration some more, you find interesting things that they're not all that surprising either from other pieces of mathematics. Now, I promised one algorithm. It's not new in any real way, but it actually works. So if you take a rational function and expand it in a partial fraction decomposition and integrate term by term, now it works. Because if you normally do this, this integral, especially when it's improper, tends to be divergent left, right, and center, because you're integrating over singularities. And in fact, you tend to, in computer algebra system, they tend to work really, really hard not to do the full partial fraction decomposition. They actually use the Hermite decomposition, all sorts of other things, because this doesn't work. Because the limits that you end up having to compute, they all diverge. It doesn't matter. It doesn't matter at all. You integrate it this way, and they all cancel out, and you get the answer that you wanted. That's nice. I think that's nice. However...
So you don't need to do the Hermite generalization?
However, if somebody like Victor Moll was here, Victor, right? His name? But what happens is, in a lot of these integrals here, there's some interesting Galois stuff going on. And partial fraction breaks it all up. And all of these algebraic dependencies of the roots. If this integral, for example, has a really nice integer answer, this one will not. It's going to have a big, big mess of algebraic numbers. Of course, they're equal, but the reason they're equal involves a whole lot of extremely complicated algebraic computations. So it works, but if you had a whole lot of structure in your R, what you've just done is break it all up the wrong way. So that's not necessarily a good idea. But now, the one thing I can say is I can make this work all the time. And there's no side condition of, well, except this case and that case and that case. No, no, no. This is always true. Which, you know, it's the kind of theorem I like. It's always true. So one of the big things is thing to look at quite seriously is that I've used the dumbest possible summation process here, which is great if you're doing theory, because it doesn't matter at all. If you change this to some other summation process and use a good one from numerical analysis, you actually improve things. You need less sample points. And this is, what happens is this H is very, very, very sensitive to the summation process. Again, no miracles. When we have divergent series, if you look at Cesaro summation or Abel or whatever these are, and you're not allowed to reorder things. So you don't get anything for free. So this depends on that. For convergent things, things like Gauss-Krumrod is really, really good. It's going to give you a great H. I'm still exploring for divergent things, which are the summation processes that actually give you better answers. And it may well be that some of the traditional ones for convergent functions are actually not the good ones. And I'm still playing around with that. That's still kind of open. One more thing that's open. I'm going to finish just on time. If you remove that. Integration by parts. There's no such thing as a good summation by parts. I have, like, integration is linear and it has all these, you know, various ththings work beautifully, but there is no analog of integration by parts when you're looking at the speed. Maybe there exists such a thing, but I have no idea. Because what I'm looking at is the speed of convergence of my integration process. And it doesn't seem to behave nicely with respect to what we usually do with integration by parts. That seems to be one of those theorems that goes away. Is that good? Is that bad? Is that the right thing? I don't know. It's a little odd. However, so the question is, you know, what kind of approximation processes are good? And what kind of, you can flip the idea around. I'm integrating a function f. Are there certain approximations to f that behave really well with respect to certain summation algorithms, so that you kind of have some nice commutation rules that you know that a beautiful approximation will then have an integration process that converges nicely, or at least whose symbolic expression works nicely. So maybe the approximation process you're interested in is one that has nice commutation law with respect to the usual symbolic computation expressions. So we know that for summation, rather than using power series, we much prefer following factorial extensions. Then everything works beautifully. Well, maybe somewhere in that direction there's something interesting to explore. Yeah, actually, I mentioned everything. I'm done.
Jacques, we're very happy to answer questions in private. If you'd like to join us for dinner, please let me know right now. Thank you.